So this is our question. So can you draw? So let me explain to you a little bit about the root locus. That in order to draw the root locus, you need to have certain kind of open loop and closed loop information. So before that, I want to show you. So if I go over here and grab this root locus methodology here, let me grab this. Okay, this one. So this is figure 10-40 in our book chapter, and I want to draw the closed loop um, equation from here, the block diagram. This is a block diagram of a closed loop transfer function. So if I do the math here, the closed loop transfer function is output over input in terms of the Laplace domain, that is equal to g of s over 1 plus g of s h s. This is our 10-33. So the characteristic equation, which is this one, this is the characteristic equation. Let's assume this is in an Laplace domain rather than writing s every time. We just write down the big letters, and that is the equation equated to 0. And this is the equation of the root locus. So the denominator in g gh equals to -1, and the angle of gh, what is the angle of -1? It is 180 degree. We call this as the plus minus 180 to 180 degree. So I'm gonna write down plus minus 180 degree, but it could be the multiple of 180 degrees, like k. If I plug in k equals to 0, then angle gh would be equals to plus minus 180. Either if you go from in the Laplace domain, either if you go from positive real axis, which is plus 180, or if you go to the clockwise direction, negative 180 degree, you reach over here for this pole location. Usually the poles are represented by the crosses on the Laplace domain. This is a Laplace domain, which is actually, I'm not sure what is happening. So Laplace domain, it is real, real plus imaginary part. So, and if it is 0, then this is the case. But if it is more than 0, like 1, 2, 3, and so on, it will end up going to the -1, because g of gh equals to magnitude is -1. -1 is on the left hand side of the real axis. And then this is known as the angle criteria. Let me erase this portion. This is known as the angle criteria, which should be fulfilled to locate the uh, uh, root locus in the Laplace domain. So you will see this condition should be met in order for the locus to have the root on it. And another criteria is this one, which is also known as the magnitude should be equal to 1. This is known as the magnitude criteria. So an S is on the root locus if the magnitude and angle criteria are satisfied. in the closed loop transfer function. So suppose if this is if suppose this equation, if I write down this equation in the form of what we call poles and zeros. The poles and zeros, these are certain terms. Like if you have k, a transfer function, I would say numerator and denominator. I would say like numerator and denominator, and numerator, it is equal to zero, and numerator can be the roots of the, or the factors of the polynomial z1 plus z2 dot dot dot, and denominator can be factors of roots in the Laplace domain, poles 1, pole 2. Okay, so now we, this is also the representation of the root locus equation. So now we come back to this question. Let's solve this problem, and this will clarify most of the root locus problem. So now, if I were you, I would start from the, uh, let me draw the straight line here. So this is my straight line. So we call this a real axis, and this is imaginary axis. Real can also, some books, or in our books, this is sigma plus j omega. J omega, I would say j omega sub d, because this is um, damped natural frequency. So s equal to sigma plus j omega or j omega t. Now, how will you locate these poles onto this Laplace plane? You will see s is equal to, the first root is located, first factor is s equal to 0, second factor s plus 1 equal to 0, that means s is equal to -1. Third factor is s plus 2 equal to 0, that is equal to s, so -2. So I'm going to cross showing you the root locus at location 0, at location -1, and location -2. So these are the poles on open loop poles. We also call this as open loop poles. And in this case, there is the H value, like H, in this case, H is considered as 1. So we don't need to worry about H in this case. Now, if I take a test pole, so, so let me show you. If I take a test pole here, and locate it over here. Suppose this is my, let me change the color here. If I take the, okay, let's take the other color here. So we want to see whether this side of the pole is on the root locus. So what is the angle? If you take a look, the angle from here to here, and from this pole to this pole, this is the test pole, okay, from this pole to this. So all the angles, so angle with s minus s0, it is 0. Angle with, this is my test pole, I would say this s super 0 is test s1 minus s0 equals to 0 degree, and s2 minus, this is my s2, this is my s1 s2, so s2 minus s super 0 equals to 0 degree. So but we know that the angle criteria should have 180 degree, plus minus 180 degree, and the odd multiple of that. Odd multiple is 2k plus 1, This is k goes from 0, 1, 2, and dot dot dot. Now, in this case, if we add all these, so what are the angles? So angle criteria, in this case, get k or like a s. So so in the angle, I'm gonna write down 0 degree minus angle s 0 minus 0 minus 0. So this is all minus 0. This is not equal to plus minus 180. You might be asking, Professor, what is this 0 degree coming from? So if you take a look, the angle for this constant is 0. So the numerator, the angle of the numerator polynomials, actually this is not, this is just a constant. So they are positive values. The denominator, when you bring it up in the numerator, like if you have e to the j theta 1 and in the denominator e to the j theta 2, so the angle in the numerator are positives, and you bring the angle from the denominator is similar to this one. The denominator angles are, when they are written in one line, they are written with a change in sign. So that's why I put negative with for the pole, all these three. So it is not equal to -1. So let's test another pole. So I'm gonna copy here. I will show you a technique very easy to start the root locus after this. So let me show you. So if we take the test pole here, and let me move these arrows away, and I want to put the test pole rather than here. I want to bring the test pole here in this location over here, and do the process here and see whether do we get a negative or positive 180 multiple. So let me show you here what is the angle. So from the angle between the first test pole, so you see the angle here, it is positive or negative 180 degree. Let's say if we go from positive, real axis is positive 180, but for this one it is 0. This one, it is a straight line. So we get our answer as one, either positive 180 degree, and in this case, this area between the two poles lie inside the root locus, which is the area on the real axis. I'm not talking about the on the plane right now. I'll talk to you about the how do they leave the plane of the real axis. So but I'm just showing you how will you find out. So this, it means this region is inside the root locus. Any test pole here, here, they are fulfilling the criteria plus minus 180. Now let's test this pole here, and I want to show you that if we have another test pole here, um over here, let's grab this one. I want to just delete this one and bring the test pole over here. Okay, and then I can just bring this one over here. So let's erase this one. So the angle for this pole is 180, for this pole it is 180, for this pole it is 0 degree. So it is plus minus 180 times 2. So it is not inside, it is not fulfilling the criteria of the odd multiples of plus minus 1. So this region is not inside the root locus region. But this region, it is inside the, yes, this region all the way, it is not inside the root locus. So this we have concluded by using the test poles on the real axis only, that if we keep on moving the test pole between two poles and away from the other poles, so to see the where is the pole. This is one method. Another method I want to show you, which is quite easy and is a little bit a trick, and I want to show you this trick here. So if suppose this is my Laplace plane, okay, and I want to change the, so this is my zero pole at zero location, pole at -1 location, pole at -2 location. This is my imaginary line j omega, and this is my real line. So in order to do that, you will put your pen down, put your pen down only when you see odd poles or zero, poles or zero. uh, Put the pen down, put the pen down. So if I drag the pen here, it's not all. As soon as I see hit the first either pole or zero, either first pole or zero, I'll bring the put the pen down. So let me show you with a different color. So when I see the hit the first pole, odd or odd pole or zero, I'll put the pen down. As soon as I touch the even number, pole or zero, I will lift the pen up, but and then I will put the pen down again, the next odd pole or zero. So this is my root locus. So you see, this is my odd pole, and this is my odd pole. Sorry, this is three, pole number three. So this, so as soon as you hit the odd pole or zero, you put the pen down and then lift it when you hit the even number of poles. You see my point? So this is how you will complete the, rather than going all this calculations, you can use this technique to solve for the real axis load locus. Another formula here, how to find out the location of the location of centroid sigma A. So what is centroid means the asymptotes. What are the asymptotes? Asymptotes are the lines which go to the open loop zeros. Let me show you how many zeros are in this open loop transfer function. So you can check. Look, there is no zero. There is no zero in the denominator numerator. There is no root for of s. When there is no root of s, then means all these three poles, they will go to three asymptotes which lead to infinity, where the poles are placed. So we need to have three um, poles, because n minus m, n minus where n equals to, where n equals to number of poles, and m equals to number of zeros. There are, in this case, there is sorry, there is no zero, but there are three poles. So we have three asymptotes, number of asymptotes. And how will you locate the, of course, they are somewhere on this line. I know, because either here, we don't know, but we will find our exact location using a formula. So what is sigma A equals? So sigma A equals to summation of all the poles minus summation of all zeros divided by the difference of their number values. So how many poles, what are the look at here. There are poles, three poles, like one is 0, other one is -1, third one is -2. So I'm going to add all these three poles: 0, -1, -2, minus, we have 0 pole, sorry, 0 zeros. So divide by n-3, which is 3, and -3, it is 3. So -3/3, it is equal to -1. It means our centroid is located right over here. Now the next part is, we need three angles to locate three lines which are asymptotes of. As I mentioned, the asymptotes are required according to our mass, that the root locus, when we increase the gain, the root starts moving from open loop holes, and they go to open loop zeros. So, and then let's find out the angle of asymptotes. So I would say use this formula, that is equal to plus minus 180 2k plus 1 over n minus m. This is the general formula. So let's, for our case, what are the angles of asymptotes? They are equal to plus minus. Let's assume k is from 0, 1, 2. Each time when you plug in 0 here, you get two answers. So plus minus 60. So we need three angles. So we already have found two angles. So angle 1 and 2. So angle A, 3 and 4. Let's do plus minus 180. When you plug in k equals to 1 here, you get 3. So we have found four angles, two from here, two from here. So that is sufficient. You will see they will keep on repeating again and again. So that is sufficient for our location. So I'm gonna draw plus minus 60, a line at angle of 60 degree here. This is plus 60, and third line is plus minus 180, which is starting from centroid to negative infinity. So this is my plus 60. This is my negative 60. So this is the case, and you will see that the root locus will start moving along these asymptotes, where when the gain goes to infinity, when the gain is infinity, the poles are, they reach the open loop zeros. And now you will see there is an imaginary line. As soon as the poles, they move into the right half plane, then e to the plus st. If you see plus st, like value of s is positive, as soon as it is positive, the system behavior becomes like uh, exponentially, it starts growing and unstable. We call this as unstable dynamic system. It should stay here before, behind the, or below the imaginary line. So s should always be negative value, and you should have negative s t in for the stability, I would say, for stable system. So this is important. There can be a question, what is the gain value so that the system remains stable? The range, we can talk more about it. So let's do one more thing here. What is the breakaway point? Where will the poles, they break away somewhere in between this region? So let me grab. So what is the next small section in the root locus design is the breakaway point. the poles never overlap each other. They have their own trajectories. When they in the real axis, when the gain starts increasing, the pole starts moving. One will go up, other one will go down. So we have to see how will they uh, maybe like this. I will show you in a bit that what is the breakaway. This is the breakaway point. And how will you find out? The equation of the root locus is 1 plus gh equal to 0, and gh can be written in the form of polynomials k or s plus 1, s plus 2 equals to 0. And from here we have to define k. Take the k on the left hand side, and you are left with negative s plus 1, s plus 2. And now you have to differentiate k with respect to s. So how would you differentiate? If you multiply, expand this polynomial, it will be like if you take the differential here, d of s, negative sign is outside, s cubed plus 2s square. I will say this is 3s square, right? This is 3s square plus 2s. So you can verify whether when you multiply you get this answer. So what is the differential of this? It is 3s square. Negative is outside. The differential of this one is 6s. The different time derivative, oh sorry, the position, the differential for this one is 2. Now you have to equate it. This dk over ds should be equal to 0. So the negative sign is distributed to 0 side. So you are left with s square plus 2s plus 1 equal to 0. And if you do the MATLAB code, what is the root of, I'm sorry, there is some equation, there is a problem here. Let me show you again. This is not correct. This is not equal to 1. So let me rewrite here the whole equation. So you can find out the poles using the Laplace this in MATLAB, the equation, or you can help me. If you do the math, you should get s1 equals to negative 0.42. These are the breakaway points. S2 equals to negative 1.57. And in our case, look, in our case, this pole is located at 0, this pole is located at 1. The third pole is located at negative 2, and this is the negative real axis. In our case, the root locus is lying in between this region. So this value is neglected, and we will take this negative 0.4. Now, guys, this is our point, and I'm going to draw the lines for the asymptotes here. And now I'm going to draw the root locus. How will you draw the root locus using this information? So imagine you have this question in your quiz. This is my root locus, okay? And the third root locus is lying on the real axis on the negative. So after beyond the negative 2. So this keeps going as k increases to infinity. So k increases to goes to infinity. K goes to, I will say, infinity. So this one. So this is our root locus. Now this point is very important for to determine what is the k value. Find k value at, we call this as imaginary crossover, at s equal to j omega. So in that case, what you have to do, you have to take this equation. So I'm going to take this equation, root locus equation. Again, this my main equation is this one. Okay, I'm going to take this equation, and or let's take grab this equation here. Look, I'm going to take this equation and find out, replace s by j omega. So I can rewrite here in this form, 3s squared plus 2s. What you have to do here, replace s, since we have to find out the at k at location j omega, replace s by j omega. So wherever you see s, you will plug in j omega there. So I'm gonna replace this by into this. This is our root locus equation. Okay, so plus 3 times 2 times. Now guys, this is a real and imaginary uh, parts together in this equation. So what you have to do, separate the real part from imaginary part, and do the work. So let's first of all open this. So this would be j cube, j to the power 3 equals to negative j. This one, j square equals to negative 1, and j of course will remain this. So can I write down like negative j omega cubed? This is negative 3 omega square. This is positive 2j. Now you have to separate the imaginary parts. Let me write down real parts here, imaginary parts here, and equate them to 0. So from this equation, we have to separate the real. So every term which has j in it, they are imaginary terms. So negative omega cubed plus 2 omega equals to 0. And every other term which does not have j, they are real terms, k minus 3 omega squared. So you have to equate them to 0. And from when you equate this, you get k equals to 3 omega squared. And from here, what do you get? From here, you get negative, or let's say omega square. I will say omega square. Let me write down here. Omega square plus minus 2. Now you can plug it in over here.
Shouldn't there be three roots for omega?
3 roots.
Yeah, it's omega cubed, not for the imaginary.
This one.
Yes, shouldn't there be three roots?
Yeah, I actually cancel it out.
Uh, gotcha. Okay, sorry.
So I simplified it over here.
Yep, you're good.
Now, guys, this is k. You see, k, it is equal to the threshold of k, the gain value. Let me show you the threshold of k. When you move the poles, the k value over here, it is equal to c. And remember, the complex conjugate pair, they have the same gain value at the imaginary crossover. That's the beauty of the root locus, that the what we call this is a complex conjugate pair move symmetrically about the x-axis. Now, the next thing it is asking you, how will you find out if zeta equals to zero point 0.5? In the question, let me show you the question again. So over here, the question states, yes. Let me reread the question for you. Consider the system shown in the figure. The figure is Did I show you the figure? Yes, this is 10 dash 40 and this is 10 dash 41, 40 and 41. Yeah, let me show you the figure. Probably I showed you a general figure. This is the real figure. So this is the actual figure for which we want to find out the root locus, and we want to locate the k value or locate the crossover, imaginary crossover. Plus we want to know what is the damping ratio. If you have a damping ratio, where is the uh, what are the roots of the crosser. So right now they will cut somewhere here, but how would you know that? Remember, there is a this angle is beta, and remember, if zeta equals to zero point 0.5 in our case, suppose, so it says find out the closed loop poles when zeta equals to zero point 0.5. So we know that beta equals to cosine inverse zeta, so that is equal to 60 degree. So if this is 60 degree here, the other line you have to draw negative. Let's focus on this first line over here, and it touches here. So how will you find out the roots at the poles at this location? So S equals to x plus j y. So let me show you what is this. Like, can I write down? Suppose this is my jy, this is my x. So I'm showing you that S, which is our desired, I would say S sub D, desired pole location, that if we have this system located at this pole, our system will have zeta equals to zero point 0.5. This we have to design our whole system such that the zeta should always be equal to zero point 0.5. Half value. If zeta is less than 1, it means it is underdamped system. If zeta is greater than 1, it is overdamped system. If zeta is 0, it is undamped system. Means, look, for undamped system, look, there is no damper. And if you keep moving a mass back and forth, it will keep on moving back and forth all the time because zeta equals to 0. But here zeta is less than 1. What will happen? For the undamped case, it will keep on oscillating undamped when zeta equals to 0. But in our case, for this case or for this case, zeta, if zeta equals to zero point 0.5, so what will happen in this case, that it will go up, comes down, up, down, and it will come to an end. So it will start oscillating, but it will have um, an envelope which will start reducing this e to the negative s sub s times t, and the oscillation part sine or cosine omega t uh, inside this envelope, which will keep on reducing the amplitude. So let's find out this desired pole location when zeta equals to so if I show you this, let me show you one figure from the book over here. Yes, this is an important for our understanding, this is an important figure. Let me show you this figure. So this figure will explain you, if the root is lying on the Laplace plane somewhere here, and you want to find out what is that location. So you can imagine that S equals to You can imagine in terms of like if this is angles beta equals to beta equals 60 degree. So let me redraw it here. If this is 60 degree, so and imagine this is my x value, this is my jy. So if this is 60 degree, what is tangent 60 equals to? Y over x. And what is y, sorry, what is y in terms of x? What is tangent 60? So let me rewrite here. I believe it is square root 3. Tangent 60 equals to, this is square root 3, it is in decimal. So can I write down like this? Y, because we know that desired pole location is x plus j omega. I want to replace y by uh, x square root 3. Can I do like this? So x plus j square root 3x. So this is my desired pole location in terms of one variable. Before that, it was in terms of x and y. Now I have simplified it. Now I'm going to grab this equation, which is the root locus equation. That like you replaced s by j omega, but now you will replace s by x plus j omega, x plus j times square root 3x. You have to replace the whole equation. Replace s equals to x plus j square root 3 times x. Now you have to plug it, and from there you will find out the gain value, and you will find out the frequency value, everything you can find out, because every location on the Laplace plane, it possesses the frequency as well as the damping. So now if you do the math here, I'm going to replace this is my x plus j omega 3 j square root 3x plus 3 x plus j square root 3 times x square plus 2 x plus j square root 3 plus k equals so you have to do the math. After you do the math here, so what you guys get, you get desired pole location x equals to negative 0.33. So I'm not gonna solve for you, but you have an essence how to solve this equation. This is our desirable. Plus minus mean the complex conjugate. So this is our root locus. This is cutting at this line like minus 0.33, and this is plus 0.578j. And similarly, the downward part is it is going to cut somewhere here. The same location, sorry, this should be same location but negative 0.578j. The complex conjugate always are symmetrical about the x-axis. Do you understand this question?
How did you solve the equation if it has two unknowns, x and k?
Oh, this is not. These are not. Look, that's a good question. This is not a one equation. Actually, this has two separate. You have to do the two separate parts. Like over
Okay,
here, you see,
gotcha. Okay.
that was a good question you asked. Students couldn't understand. Imaginary and real numbers, they are separate. So each equation which is imaginary in itself, they are actually two parts. You see, so you can find two unknowns from the real part, equate them to zero, and from imaginary part, equate them to zero. You guys probably you can do it at home, and let me know if you have any question. I believe you can solve this at home. So let's do one more problem here. And another thing I want to show you, that how would you find out the angle of departure? Sometimes there is another technique, we call it a departure angle or arrival angle. So if the poles are located inside the, so with that we have finished this example, but I want to show you the another concept here, angle of departure, I will say. So if the how would you find out the angle of departure? Because right now in this case, look, in this previous case, our we don't need to find out the angle of departure because all the poles are located on the um, real axis. But what if you have such certain situation when whether the where the open loop poles are located inside the plane, and then you have to draw an asymptotes, or how would they leave this? So we call this as suppose they come over here, touch over here. This pole is symmetrical, so it touch over here, and one goes here, one goes here. So how will you find out this angle of departure? This is our next section. The formula for the angle of departure is this one, 180. I would say let's keep it simple for the positive, the angle GH. So where the angle GH is the angle excluding that pole which is for which we have to find out. Suppose this pole we have to find out, exclude those angles at that angle specifically and find out the remaining. So similarly, the angle of arrival. Suppose you have two zeros inside the pole, and suppose this is my poles are located here, and the zeros are located inside the plane somewhere here. So how would it reach? So you would draw a line here. Suppose this is the angle asymptote. So you will join this angle of we call this as angle of arrival. Angle of arrival comes for the pole zeros. So this will be the next. Oh, this should be somewhere here. Angle of departure. You see my point? So it's a little bit difficult figure, but you can draw it in MATLAB. In MATLAB, there is a command R locus. So probably I can show you my MATLAB event talk. Somehow my MATLAB is difficult to be opened, but and let me write down the formula for the angle of arrival, that 180 degree minus angle of GH. So you can find out now the root locus in this case. I have explained you how to find out the breakaway point, and sometimes you have to find out the break-in points. Remember, breakaway points are for poles, and break-in points are for zeros. Like I said, angle of arrival is for the zeros located inside the plane, and angle of a departure are for the angle. But what if the zeros are located on the real axis? So we call this as break-in points for the poles for the zero. So if suppose this is situation where two poles and the two zeros are, so they will leave somewhere here, and one will go to this open loop zero, and the other root locus will go over here. It should be very close to this one. So this is our trajectory for the when the gain increases to infinity. So this is how I have explained quite a lot about the root locus. I think you should be good in a good position now to draw the root locus. So let's do one example here, one more example. Get the root locus of this case. So let me show you this. So this is another example. I will show you. I'll open another homework specifically for root locus. This will help you to practice more for the not this week, the following week. I will give you the quiz from chapter 6. With that, I will finish chapter 6 today. All the sensors. So let's say one more example. So GH, I'm excluding just S domain, but it is obvious this is k s plus 3. Now you can um, draw the real axis, and this is my imaginary line, this is my real line, and this is so s1 equals to, you see I drew the circle. Circles are for the zeros representation, and the crosses are for the poles representation. Now the question is, how will you draw the um, root locus for this one? So let's do the uh, find out how many asymptotes do we have. N minus m, 2 minus 1, just one asymptote. And how will you draw the real axis root locus? As I mentioned, that the technique I would follow for the pen down, pen up, from the odd number of poles or zeros. So look, you see, I keep on dragging the pen, dragging. I do not see anything. But as soon as I hit the first odd number of pole or zero, I will start dragging the pen on the real axis. This is my root locus on the real axis. You see my point, guys? This is very easy. Now I've shown you this one. You can use the test pole as well as this method. They will be equally acceptable for us. So this line is -2 for this, -2 is here, -2 is here. Now the angle of asymptotes. So what is the centroid location? What is the centroid location? Centroid location equals to, in this case, all the poles, sum all the zeros. So let's sum this pole, -2, -2. And because the other parts, when you sum them up, they cancel out because they are plus minus. Okay, they are plus minus, so they sum out. You just don't worry about the imaginary complex conjugate. Always the imaginary portion, they cancel out. Negative, the summation of this one, which is -3, and -1, which is 1. So -4 plus 3 over 1, which is equal to -1. So -1 is the location of the asymptotes as centroid, and the location is this one, so we don't. So I would say let's go to the next part. What is the breakaway and breaking point? In this case, the breakaway and breaking point, we don't need to worry about. There is no break-in or breakaway for this case, so it's not valid breakaway point, break-in point. So let's do angle of departure. What is the angle of departure? 180 plus angle GH. So let's find out the angle GH. I'm going to take this point as my point for from where I want to find out the angle. So let's take S2 as exclude at. So I'm going to take this point at S2 equals to -2 plus j square root 5. So that's the angle. So I'm going to use this one. So I know that this is my GH. So I'm going to grab this one, the whole GH here. and you will replace this s by this value. So let me rewrite here everything. So can I write down like this? Um, minus 2 plus j square root 5 plus 3. And this one, I'm going to use this as negative 2 plus j square root 5. So I'm going to exclude this one. Agreed? So negative 2 plus j square root 5. So you're left 2 square root 5. The denominator is this one. And what is the angle for this one? Let me explain to you. If this is j axis, so the angle is the pole is located over 2 square root 5 means somewhere it is on the positive. Is always the angle for this one 90 degree. The denominator angle is 90 degree. What about the numerator angle? So let's find out the numerator angle. Negative 1, sorry, positive 1 plus j square root 5. What is the angle for this location? We know that angle we have to find out. Theta equals to tangent inverse square root 5 over 1. So let me use my small calculator. So arctant square root. I got 65.9. So this is the angle um, from the numerator. So it is 65.9 degrees. And the denominator has the angle 90 degrees. So that's good. We have found this angle. So what is the net angle here? The net angle is the zero minus poles. 24.1. And the magnitude, what is the magnitude for this one? Let's say we can do the magnitude later on, but if you want, I can show you the magnitude. If this, what is the magnitude of this numerator? Numerator magnitude is square 1 plus 5 square 6, and the denominator magnitude is the same like this one. So denominator magnitude is 2 square root 5. So if you want to find out the in terms of the magnitude criteria as well as the angle criteria, so let me show you the first of all the angle for GH equals to 24.1 degree. Now let's use the angle of departure formula, which is this one 180 plus angle GH. So can I write down here 180 plus angle GH? So you will help me now. 180 minus 24, because this will be negative sign here. I forgot to write down negative sign here and negative sign here. Negative 24.1, which is 155.9 degree. And if you want to draw the root locus, sorry, these are my roots located at location negative 2 plus minus j, negative 2 plus j square root 5, and negative 2 minus j square root 5. And the angle of departure for this pole, it is positive. So positive, you have to draw a line here, and positive 155.9 let's say 156 degree. It doesn't matter, it's a little bit off. So now you can see this is the angle of departure from the pole, and that will go to end up, it will go, this is my zero location, this is my zero, this is my zero. It will go over here, and it will keep on increasing, it will join the or open loop zeros here. And similarly, you have to draw the negative 156 for this case. Negative 156 is over here. This is symmetrical about the x-axis, so it will touch here and go to the asymptote, which is going over here. So this is your answer for this question.
How do we know where it intersects the x-axis, though?
Oh, break-in points. This is the break-in point that you can find out break-in point. So if you are interested in that, I can find out for you using this the equation. So this equation, the GH equals to K. So what happens actually, the equation is 1 plus GH equal to 0, and the GH is in this form. So you plug in over here and find out K value from there. So if you do the math here, you can find out, let me write down, this is K is in the form of, uh, if you do the math, you should get this simplified version, J square, I would say plus 5. This is just the math, but the actual concept is you have to differentiate K with respect to S, and then equate it to 0. And from there, you can find out the roots of um, this polynomial. So you will get S1 equals to minus 0.55 and S2 equals to minus 5.45. And you will see that minus 0.55 is not a valid point, which is not lying somewhere here. So it is not our root locus location. So the break-in point is minus 5.45, somewhere here. You can practice at home. I have shared with you some of the handouts, and I will if not, then I'm gonna open the what we call the Dropbox for the assignment regarding the root locus questions. So as I mentioned, now let me end the recording.
I haven't looked at our homework yet, but I'm assuming it's going over root locus 16 to
Yes,
31 or something.